Hi, I'm Tousif. I'm a PhD student at the Center for Scientific Computing and Visualization Research at the University of Massachusetts Dartmouth. In this talk, I will briefly summarize the numerical relativity surrogate model for eccentric binary black hole gravitational waveforms. This work has been done in collaboration with Vijay and Jacqueline at Caltech and Scott and Gaurav at UMass. As we know that the numerical relativity waveforms are obtained by solving the Einstein equation in supercomputer, while it can produce most accurate gravitational waveforms, it is computationally expensive, taking days to weeks to generate one single waveform at a single parameter space. This means that the NR waveforms cannot be used for detection and data analysis pipeline. One remedy is phenomenological waveform models, which assume some kind of phenomenology about the binary black hole system, for example, whether it's non-spinning or precessing or eccentric, and then approximates the NR waveform. So even though phenomenological waveform model can produce faster waveform, their accuracy is not really good. On the other hand, we have the effective one-body or EOB waveforms. EOB waveforms takes faster to generate a waveform than a inner model. However, when compared with a phenomenological waveform model, EOB is much more slower, making it a bit difficult to implement for a data analysis pipeline. Inner surrogate waveforms, on the other hand, is both accurate as well as fast, making it perfect for detection and data analysis pipeline. Here we show a schematic of surrogate waveform modeling. In surrogate model, basically, it takes a set of pre-computed waveforms generated by an underlying model. For example, for our case, it's the numerical relativity model as input, which is characterized by lambda. And then once you have the waveforms for different parameter values in the parameter space, you interpolate in the parameter space between these waveforms to produce a new waveform for arbitrary parameter values. Here we construct in principle mass ratio Q equal to 1 NR surrogate model for eccentric binary black hole waveforms. We call the time domain inspiral-merger-ringdown waveform NR surrogate 2D Q1 eccentricity. The model is built with 39 NR waveforms. We have the dominant 2-2 mode as well as two different higher modes, 3-2 and 4-4. Because of the symmetry, the odd modes at 0 for Q equal to 1. All the waveforms are aligned in time such that the overall peak at t equal to 0. And then we also align the initial phase to start from 0. It makes the modeling easier. We model the dominant 2-2 mode in the inertial source frame. However, for the higher modes, we transform the waveform to the co-orbital frame where the data looks much more smooth and slowly varying, making it easier for modeling. Here we show the real part of the inertial frame 2-2 waveform and the co-orbital frame 3-2 and 4-4 modes waveform. Now, departure of the NR orbits from circularity is characterized by two different parameters. One is eccentricity, the other one is mean anomaly. The measurement of these quantities from the NR track data itself that can be affected due to the gauge effects. Because of that, instead of using the orbital data, we decide to use the waveform data itself. And for that, we use a particular eccentricity estimator proposed in Mora and Will 2002 paper, where we basically use the orbital frequency at the periastron and apastron that corresponds to the maximas and minimas in the orbital time profile here, and then use those to estimate eccentricity profile for the whole waveform. Here for waveform ID 39, we show that how the eccentricity varies with time using this particular eccentricity estimator. Then we use the mean anomaly defined as a extra phase incurred because of the presence of eccentricity in this system. The mean anomaly is a linearly varying function with time in between two different pericenters. And for our case here, we estimate both the eccentricity and the mean anomaly at a particular reference time minus 4200 m before the merger. Here we show the parameter space for our model. In the x-axis, we have the eccentricity. In the y-axis, we have the mean anomaly values. Our eccentricity ranges from 0 to 0.17, where the mean anomaly ranges between 0 and 2 pi. Finally, here comes two different important pieces of our data of our model building. So instead of modeling the amplitude and the phase of the eccentric waveform directly, we decide to model the residual amplitude and the residual phase between the eccentric waveform and the non-eccentric waveform, because the residual amplitude shown in the orange here and the residual phase shown in the right panel here, they are much more simpler and slowly varying compared to the whole amplitude and the phase. Here we show a waveform with eccentricity 0.167 and another non-eccentric waveform, and then we show the residual amplitude and the residual phase. This means that we have 6 different data pieces to model for our surrogate waveform. We have the residual amplitude and the residual phase for the 2-2 mode. Then we have the real and imaginary part for the coorbital frame 3-2 mode, and the same for the coorbital frame 4-4 mode. We follow the prescription provided in the Blackman et al. 2017 paper to build the surrogate. First, for each of the data piece, we construct a compact linear basis using singular value decomposition. We then construct an empirical interpolant in time using a greedy algorithm which picks the most representative time nodes. We then construct a parametric fits over fits of each data piece at each time node across the 2D parameter space defined by the eccentricity and mean anomaly using Gaussian process regression fitting. Here we show the Oauth error, the waveform model which corresponds to the Oauth error for our surrogate. This particular case is for eccentricity 0.154 and anomaly 2.5. Note that these values of eccentricity is near the boundary of our training range, where we do not have much waveforms to train. This is the reason why the surrogate doesn't work very good at that particular region. Now we show the real part of the H22 and H32 and H44 mode waveform here. Then we zoom the waveforms near the late inspiral-merger-ringdown part in the right panels, where the red line shows the NR data and the black dashed line shows the surrogate approximation. We see here that there is a time and phase mismatch between the NR data and the surrogate waveform. Now here we show the sky average frequency domain mismatch defined by this particular expression here using a flat noise curve between the surrogate model and the NR data. In the plot here, for a comparison in black, we show the NR resolution error obtained using the highest two resolution NR data obtained in the waveforms, and then in the red we show the surrogate error for the training, and in the violet we show the surrogate error in validation, which is basically a leave out validation, where we leave one waveforms at a time out of the training set and then build the surrogate and try to approximate that particular waveform and find the error between the NR data and the surrogate approximation, which gives a sense of the validation error. Now here we also quote the 90% credible interval for the NR error, surrogate training error, and the surrogate validation error in the log scale. What we see here that the 90% credible interval for the NR error has significant overlap with the surrogate training error. And the surrogate validation error, even though that is a bit worse than the surrogate training error, still the errors looks really good in the range of 10 to the power minus 4 and are and comparable to the other NR surrogate models for precision or the aligned spin systems. Finally, we show that the mode mixing between the spherical harmonic modes is clearly seen in the NR data. Now, in the solid line shows the NR data, whereas the dashed line shows the surrogate approximation. Now, in this particular plot here, what we can see that the significant power of the 2-2 mode that leaks to the 3-2 mode, and showing the effect of mode mixing in the blue curve here. And then we also show that the surrogate can recover the mode mixing without any extra effort. In summary, we present that the strategy that we devised here in this particular project, that is good enough to build a NR surrogate for eccentric binary black holes, and this strategy can further be implemented to make a aligned spin eccentric binary black hole waveform, or even for the non-spinning waveforms for which ranges to higher mass ratio. For an immediate follow-up, we are now working on the aligned spin eccentric NR surrogate for comparable mass ratio binaries and the eccentric binary waveform model for extreme mass ratio inspirals. So with this, I'll stop here. If there are questions or comments, I'd be very happy to address those. So kindly leave those questions or comments in the chat section. So I'd be happy to address whenever possible. So yeah, thank you very much for listening.